In this tutorial, you will be introduced to some of the basic ideas of set theory, a branch of mathematics that is concerned with relationships between collections of objects. The concepts that we will look at are highly relevant to the fields of computer science, probability theory, and mathematical proof. You will also be encouraged to think about how you use language to convey meaning. In mathematical terms, a set is simply a collection of items, known as elements. For example, when tossing a coin just once, the set of all possible outcomes consists of heads or tails. We might denote this set by the name x and write x equals h, t, where h stands for heads and t stands for tails. Notice the use of curly brackets to indicate a set. These types of brackets are called braces. Two sets are said to be equal if they contain the same elements, regardless of the ordering. So the set shown here is exactly the same as the set T, H. All elements in a set must be unique, so H, H is not a valid set. The outcomes from two coin tosses might be written as the set Y, consisting of heads, 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 tails, tails, heads, tails, tails. We can refer to individual elements from the set by using the special element notation, which looks like this. For example, we can say that HH is an element of set Y. This notation can also be used to refer to arbitrary items from a set, with an inverted A used to mean for all. So this statement means for all elements of the set Y. Notice that it is customary to use uppercase letters to refer to a set and lowercase letters to refer to individual elements. Sets can have a finite or an infinite number of elements. For example, the set of counting numbers 1, 2, 3, 4 and so on form an infinite set. There are a few important sets of numbers that you should be familiar with. You need to be able to recognize the names of these sets and the notation used to represent them. The counting numbers are called the natural numbers, n. The positive and negative counting numbers, together with 0, form the integers z. The integers can be used to form the rational numbers q. And by taking the rational and irrational numbers together, we get the set of real numbers r. Later you will learn that the real numbers are themselves a subset of the complex numbers. The font that's used to represent these sets is called Blackboard Bold, or is also known as double struck. We will look at the relationships between sets and ways of combining them to make new sets. The union of two sets refers to the collation of distinct items from both sets. This can be represented graphically in a form called a Venn diagram. The circular area on the left represents the set X, and the circular area on the right represents the set Y. The shaded area shows the union of the two sets. Using element notation, we can write that X union Y is the set of elements Z that are either in X or in Y. The colon symbol is usually read as such that. Notice that the logical OR operator includes the possibilities that Z is in one or in both of X and Y. This is similar to the way that OR is used in computer science, but it may not be the same way that you use the term in everyday language. For instance, if I ask you the question, do you like the colour red or blue, what would you respond? A logical response would be to say yes or to say no. We can see from the diagram that set union is commutative, that is to say that X union Y is the same as Y union X. By way of example, let's suppose that we have the sets X equals 1, 2, 3 and Y equals 2, 3, 4. The union of these two sets is the collection of elements 1, 2, 3, 4, because that's all of the items that are either in X or in Y. The intersection of two sets x and y refers to the shared elements from both sets, and is represented graphically by the shaded area shown. Using element notation, we can write that the intersection of x and y is the set of values z such that they are in x and in y. The intersection is also commutative. For the sets given here, the intersection consists of the elements 2 and 3. The complement x bar represents all elements that are not in the set X. Graphically, the complement of X is the area outside the set. The elements in the complement depend on the elements in the universal set, which might be the set of all counting numbers, for example. The complement can also be written using a superscript c instead of an overbar. The set difference x minus y refers to all elements that are in x but not in y. We can also write this using element notation. The set difference lends itself well to the subtractive notation, since the area enclosed by y is removed from the area enclosed by x. For the example case, the set difference x minus y is the element 1, since that's the only element in x that's not in y. Notice that the set difference is not commutative. For this example, y minus x is the set containing the element 4. The set difference is also commonly written using backslash notation, as shown here. Now we'll have a look at some examples to test out what we have just learned. Pause the video and try to decide which of the expressions shown are equivalent to the set difference x minus y. There may be more than one answer. Press play when you have decided your responses. The correct answers are 1 and 3. Hopefully you realise that answer 3 is just the direct translation of the statement in x and not in y. The other statement might be easiest to consider graphically, starting with the intersection of x and y. Then, x minus the intersection is a set of values that are in x but not in the intersection. Let's have a look at the areas given by the other two statements. The set x union y complement contains all of the x values, as well as any values from the universal set that are not in y. The complement of the intersection of x and y is a set of all values that are not in the intersection. Now pause the video again and try to work out what graphical region is represented by the union of set differences x minus y or y minus x. Press play when you are ready to check your answer. In this case, we have everything that's in x or y minus everything that's in both. This operation is called the exclusive disjunction and is known as XOR in computing terminology. For the two sets x and y that we've been using, the exclusive disjunction gives the result 1, 4, since the union is 1, 2, 3, 4, and the intersection, which is removed, is 2, 3. The symbol shown is often used to denote the exclusive disjunction of two sets. Another useful symbol is the subset symbol. The expression written here states that y is a subset of x. That means that all elements in set x are also in set y. We can also say that x is a superset of y. An example case might be where x equals 1, 2, 3 and y is the set 2, 3. In element notation, we can write that if z is in y, then z is in x. The double-struck arrow is read as implies. It means that if the left-hand side of the statement is true, then the right-hand side of the statement is also true. The subset symbol includes the possibility that x and y are the same set. We are allowed to drop the line from under the symbol to indicate that y is a strict subset of x. The notation is very similar to the way that we distinguish between the strict inequality less than and the non-strict inequality less than or equals. A strict subset carries the additional requirement that there exists an element which is in the superset but not in the subset. The backwards E symbol is used to mean there exists, so this statement is read as there exists an element z in x such that z is not in y. It is worth noting that for two sets x and y to be equal, we require that x is a non-strict subset of y and that y is a non-strict subset of x. This fact is often useful when proving that two sets are equal. The double struck arrow, which points both ways here, means implies and is implied by. It means that if the left-hand side of the statement is true, then the right-hand side is true. And if the right-hand side of the statement is true, then the left-hand side is true. To finish off, we'll have a quick look at interval notation. Square brackets are used to denote the endpoints of an interval of the real number line. This is the same as using a non-strict inequality. A round bracket is used to represent a strict inequality. Intervals represent sets of values, and so they can be combined using the set operations that we have seen. For example, the union of the intervals 2, 4 and 6, 8 means a set of real numbers that are between 2 and 4 or between 6 and 8. Because square brackets were used here, the values 2, 4, 6 and 8 are included.